So we're going to take a dive back into vectors for a little bit. What we're going to do here is go through one of our two operations that's considered multiplication of vectors. So this first operation we're going to go through is called the dot product, because if you think usually a dot represents multiplication. And then the second operation we're going to go through next is going to be the cross product, because you can also use an X to represent multiplication. But it's not quite what you normally think of for the sense of multiplication, because these vectors are a little bit different. So we're going to start with what is this thing? So if we have the vector A, which has components A1, A2, and A3, and then the vector B has the components B1, B2, B3. Then the dot product of A and B is defined as the follows. So it's the dot product, so we use the dot, which is like our multiplication. But what we're going to do here is we're going to multiply like components. So A1 and B1 are in that first component. So we're going to multiply those two values together. Then we have A2 and B2 in the second component. So we're going to multiply those two values together. And then finally, we have A3 and B3 in the last component. So we're going to multiply those together. And what we're going to do is we're going to add these numbers up. So this is super important here. A1, B1 is multiplying those first two numbers. You're adding another real number and adding another real number. So the result of this is no longer a vector. Instead, what you're getting is a real number in the end. So this is super, 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 super important. A dot B is not a vector, but rather a scalar. Okay, so when you go through the dot product, the resulting thing should just be a number in the end. It's not like when I add two vectors, it gives me another vector. When I subtract vectors, it gives me a vector. Here, when I'm doing the dot product, the result is a number. Now again, like it's common in math, we have a lot of different names for the same exact thing, and it really just depends on the context of the problem, which notation is going to be used. So sometimes you may hear the dot product referred to as the scalar product because it results in a scalar, or you might also hear it called the inner product. And this is a concept you'll go heavily into in linear algebra, but they both mean the same thing. So let's do a quick example. Let's go ahead and say if A is the vector 6, -2, 3, and B is the vector 2, 5, -1, then if we find the dot product of these two vectors, A dot B, we go ahead and multiply like components. So in the X spot is 6 and 2. In the Y spot is -2 and 5. And Z is 3 and -1. And then we just add these together. So this is 12 minus 10 minus 3. So the resulting dot product between these two vectors is just the number -1. So why it's called the scalar product, it results in a scalar number, not a vector. So to give you just insight, when we do the cross product, that will result in a vector instead. So since it's a new operation, we're going to go ahead and we're going to go through all of our different properties. I'm going to at least show you proof of one of these. It's the one that we're going to use the most frequently. So let's assume A, B, and C are vectors. And D is a scalar. Then the following properties hold. The first one is the one that I will prove. If you take a vector and dot product it with itself, what you're really doing is finding the magnitude of that vector squared. If you do A and dot product it with B, this is commutative, so it doesn't matter the order that you do this in. Third one, if you want to do the vector A dot product with the sum of the vector B and C, it does distribute, so you can do A dot B plus A dot C. Fourth one, same thing holds if you're doing scalar multiplication. So if you do the scalar D times the vector A, and then you want to dot product it with B, you can instead do the scalar multiplication after we do the dot product, or you can move the scalar to the other vector. Doesn't matter. And then the fifth and final product, if you take A and dot product it with the zero vector, think of the zero vector as 0, 0, 0. Anytime you take the first component and times it by 0, plus the second component times 0, plus the third times 0, the result of this is always going to be the number 0. Because again, this results in a number. So I think some of these are relatively straightforward, or hopefully they seem like they would make sense. What I am going to do is I'm going to show you this first one is true, because that is one that we'll use pretty frequently. So let's go ahead and let's let A have the components A1, A2, A3. Then if I take the vector A and dot product it with itself, that means I'm doing A1, A2, A3, dot product with A1, A2, A3. And then I'm going to go ahead and multiply like components. So we do the first multiplied by each other. So that gives us the first component times itself, which is just the first component squared. Then we move on and do the second, A2 times A2. So it is really A2 squared, and we're adding that on. Then finally, the third is A3 times A3. So that is A3 squared. And you can see this looks a lot like our magnitude formula, except it's missing the square root. So I don't have this to find the length of the vector. So since that's missing, all that means is it's the magnitude squared, because we know the square and square root undoes each other. So you might be thinking, what does this number do? Why is it important? Why do we need this? Well, we're going to start by geometrically why this particular property or product is important to us. And then it's going to lead into what that number will tell us as well. So we're going to start geometrically. What is the purpose? And geometrically, the dot product appears when we try to find the angle between two vectors. So maybe in your pre-calc class or trig class you saw this. It really just depends on if you had time to go over. But we're actually going to derive where the formula for the angle between two vectors comes from. So we're going to let A and B be the two vectors we're looking at. So we'll let A and B be two vectors. And we're going to let theta be the smallest angle between them. So i.e., we're going to assume that this value of theta is between 0 and pi. The reason for that, to just give you a visual, if here is our vector A, here is our vector B, you technically have two angles. You have a bigger one here, but we want this smaller one. This is what we're considering theta to be. So those two angles would add up to 360 degrees. So theta is the smaller value. So what I'm going to do is I'm going to draw a picture as to what's going on here. So we've got our three-dimensional surface. So we're going to draw our x, y, and z components, our axes. And then our vector A, let's say it starts at the origin and it goes to, let's say here. Here is A. And again, I can't tell if that's necessarily in the xy plane. Sure, it might look it, but it could be up as well. And then let's say our vector B is right here. Then the angle between them is this angle, which we're calling theta. Okay. The vector A, we're going to say has the components A1, A2, A3. And then the vector B, got to make sure my notation is right, that I put that bracket. B has the components B1, B2, B3. Okay. Well, one way that I can figure out the angle between these is by introducing some kind of triangle. So I'm going to go ahead and I'm going to close this triangle here. And let's say that this triangle or this vector here points down. So remember, this vector out this way would be A plus B. When I go ahead and connect the dots, this would be the angle A here, or A. And then if I go backwards, this would be negative B. So this resulting vector is actually going to be A minus B. So we've got a triangle. No idea if it's a special triangle. It may be right. It may not. We have no idea. So what I want to do to be able to find the connection between this angle and these different sides is use one of our special triangle formulas. So I'm not going to do the law of sines because I don't know other angles here, and I'm only concerned about this particular one. So what we're actually going to use is the law of cosines. So it's probably been a long time since you've used this, but this is a way to relate one angle to all of the side lengths of it. So these two come in a pair, the angle theta and the side across from it. So if you remember the law of sines, it was like, here's our triangle A, B, C, and here is the angle theta. Our law of sines was that C squared is A squared plus B squared. So kind of like our Pythagorean theorem, but then we subtract 2AB times cosine of theta. So this angle was the angle across from side C. So I'm applying the same kind of idea here, except instead of side lengths, I'm using the magnitude of our vectors. So applying the law of cosines, in this case, my side is the vector a minus b. So we need to find this length and square it. And then on the right-hand side, this will be side a, so it's the magnitude of vector a squared, plus the magnitude of vector b squared, and then minus 2ab, but again, the magnitude of these vectors, times cosine of theta. Okay, and theta is exactly the angle between A and B. So now we can go ahead and get rid of this. We don't need our law of cosines anymore. So what I'm going to do is I'm going to manipulate this formula because I really just want it in terms of A and B, not this A minus B. So we're going to actually work with this. So I want to figure out, does this simplify? Does it work a little bit nicer? So let's further dive deep into this. Let's look at the magnitude of A minus B squared. So remember, if I have the magnitude squared, back to this property that we proved, it's really the dot product of A minus B with A minus B. So the vector A minus B, dot product with A minus B. Okay. The vector A minus B is just the one where the components have been subtracted. So the first component is A1 minus B1, A2 minus B2, A3 minus B3. And I'm going to dot product that with exactly the same thing. And then we go ahead and we multiply like components. So let's make this a little bit bigger. When I take A1 minus B1 and multiply it by itself, that is just this quantity squared. Likewise, when I multiply the second component, because it's the same exact thing, it is A2 minus B2 squared. And then last but not least, A3 minus B3 squared. And because these are just numbers, we can go ahead and we can FOIL these things out. So this gives us A1 squared minus 2 times the product, A1, B1. And then we get the last term squared. When I do the same thing for the middle term, you get the first term squared minus 2 times the product, and then plus the last term squared. And then finally, you get A3 squared minus 2 times the product plus the last term squared. So from here, what I'm going to do is I'm going to group those like pieces. So we've got A1 squared plus A2 squared plus A3 squared. Those are all important. And the reason these are important is because this is exactly the length of A squared. So this is the magnitude of A squared. Then keeping the same idea, B1 squared plus B2 squared plus B3 squared is exactly the length of the vector B squared. And then finally, let's see, what color haven't we used? Don't really have a nice one. We'll go with green again. You got minus 2, A1, B1, minus 2, A2, B2, minus 3, A3, B3. They all have a minus 2 in common, so I'm going to go ahead and factor that out, and we're left with this. And if you look at that, that is multiplying the like components from vector A and B and adding them together. It's exactly the dot product between A and B. So what happens is this formula actually simplifies really nicely as the magnitude of A squared plus the magnitude of B squared minus 2 times the dot product of A and B. So it actually kind of, in a sense, you can think of FOILs out because you get A dot A, which is the magnitude of A squared. You got minus B dot minus B, which turns into positive B squared. And then you've got minus A dot B minus B dot A. It really gives you two of them. So it's really like you've just FOILed this out in a sense. So instead, on this left-hand side, I'm going to replace this formula by this one here. So what this gives us is on the left-hand side, A minus B, the length of that squared, is really the magnitude of A squared plus the magnitude of B squared minus 2A dot B. And the right-hand side, we've done absolutely nothing with. It is the magnitude of A squared plus the magnitude of B squared minus 2 magnitude of A, magnitude of B, cosine of theta, and theta is the angle between A and B. So just simplifying this a little bit, if you go ahead and subtract this, those cancel each other out. And same thing, these two cancel each other out. So it really leaves us with negative 2 times the dot product of A and B is equal to negative 2 times the magnitude of A, magnitude of B, cosine of theta. And then when you go ahead and you divide by negative 2, that cancels out. And this tells us if I take A dot B, it's equal to the length of A times the length of B times cosine of the angle between them. And so this is our really important formula that tells us how we can figure out the angle between two vectors. So if I have vector A and I have vector B, I can easily take their dot product. I can easily find their length. That will tell me cosine of the angle between them. So rearranging this is the same thing as saying that cosine of the angle between A and B is equal to the dot product of the two vectors that form the angle over the magnitude of each of their lengths. So these are important formulas for us. So you can see our dot product is going to be essential because the way that these two angles connect is important. And again, when you're dealing with a lot of forces, that's where this comes into play too. So this helps us out a lot. So let's try an example. Let's find the angle between two vectors. And then we're going to work in 2D here, but again, the same thing holds for 3D. So we're going to find the angle between the vectors A and the vector A has the components 1, 1, and the vector B, which is 10, 0. So I've got to find a couple things before I can figure out what the angle is. Let's go ahead and start with the dot product between these two vectors. So again, that just means I'm working component-wise, which is 1 and 10, and then 1 and 0. So we do 1 times 10 plus 1 times 0. I don't need those parentheses. So the dot product between these two is 10. If I go to find the length of A, that means we take the components squared, add them together, and take a square root. 1 plus 1 is 2, so the length of A is root 2. The length of B is 10 squared plus 0 squared under a square root. Well, that's the square root of 100, so the length of B is 10. So plugging this into our formula, cosine of the angle between A and B is equal to the dot product over the magnitude of each vector. The dot product is 10, the length of A is root 2, and the length of B is 10. The 10's cancel, so this gives us 1 over root 2, which you're not used to figuring out what angle gives you 1 over root 2. So if you rationalize this by doing root 2 over root 2, this simplifies to this. So remember, rationalizing means taking top and bottom and multiplying it by that radical. So this way the radical cancels in the bottom. So what we're ultimately saying is that cosine of the angle between A and B is equal to root 2 over 2. So you're trying to figure out what angle this occurs for. The other way you can think of this is because we're dealing with an angle between 0 and pi, we can say theta is equal to arc cosine of root 2 over 2, which in that case, the only angle for cosine that will output root 2 over 2 is in quadrant 1, and this angle is going to be that 45-degree reference angle, which is pi over 4. If it happened to be that this was negative, that would mean it's the angle in quadrant 2, so that angle would be 3 pi over 4. So again, you want to be very comfortable with your trigonometry at this point. Okay. All right, so now that we have a little bit of practice with that, now the other nice thing that results for this formula is if your angle in here is, say, pi over 2 or 3 pi over 2, then cosine of that is going to be 0. And so when an angle forms a right angle, immediately that's going to tell us that this piece is going to have to equal 0. So we have another word that we're using now to talk about perpendicular stuff. So we say that two vectors are perpendicular or the more appropriate terminology now is orthogonal. If the angle between them is theta, which is pi over 2. Because again, we like the smallest angle. So the only other right angle would be if the two vectors here are this, or it's 3 pi over 2. So they represent the same thing. So we just pick the smaller angle. So the nice thing about this is if A and B are orthogonal, then based on our formula, A dot B is the length of A times the length of B times cosine of the angle between them, but that's pi over 2. And cosine of pi over 2 is 0, so immediately you get 0. So if the two vectors are orthogonal, their dot product is going to equal 0. And then really, this is enough criteria for us. So on the other end, if we know the dot product is equal to 0, then using our formula, 0 is the length of A, length of B, cosine of theta. The length is positive, so this tells us cosine of theta has to equal 0. So immediately you land at theta has to equal pi over 2. So this is a special criteria if you remember ever learning about those if and only if statements. The dot product equaling 0 is enough justification to know the vector is orthogonal. And if the vectors are orthogonal, you immediately know the dot product is 0. So you can kind of read this sentence either way. So what we ultimately say is two vectors are orthogonal if and only if, which we abbreviate to IFF, their dot product is 0. And again, this statement means you can read it either way. Two vectors are orthogonal, then the dot product is 0. If the dot product is 0, that means the two vectors are orthogonal. So you can read the sentence as an if-then either way. And then if you think about the 0 vector, well, anytime you dot product something with the 0 vector, it's 0. So we actually say the 0 vector is going to be orthogonal to every vector. So we're going to put this in as a little note. The 0 vector is considered to be orthogonal to all vectors. So let's try an example utilizing this now. We want to know, are the vectors 3i plus 2j plus k and 2i minus 4j plus 2k orthogonal? So this is just written out in terms of I, j, and k. I personally don't like using it because it's a pain to have to write all of these out. But to determine if these are orthogonal, I'm going to go ahead and take the dot product between these two. So my first vector really can be written as 3, 2, 1. And we're going to dot product that with 2, negative 4, 2, because that's our other vector. So going through this, the first components are 3 and 2. The second are 2 and negative 4. And the last are 1 and 2. So this gives us 6 minus 8 plus 2. Well, 6 plus 2 is 8, minus 8. Indeed, this boils down to 0. So I do not need to do any other work. I don't need to figure out the angle between them. Because the dot product is 0, that's enough information for me to say that yes, these vectors are orthogonal. Okay. Now in the same kind of similar boat, we have orthogonal, meaning they form that right angle. We can also talk about two vectors being parallel to each other. So we want to go through the classification for that. So two vectors are parallel if and only if the angle between them is theta is 0, or if this angle theta is equal to pi. Basically meaning if I have one vector here in this direction, if the angle is 0, you basically can overlay it right on top. So it's pointing in the same way. If the angle is pi, that means there's 180 degrees between them. So all that's happening is this vector is pointing in the opposite direction. So if that's the case, because they're pointing in the same direction as each other, but they're just scaled, they're really scalar multiples of each other. So that's another thing we can say. So two vectors are scalar multiples of each other if and only if the angle between them is 0 or pi. Because remember, scalar multiples mean they have the same direction, and this is technically just the opposite direction, but that means you took the prior angle or prior vector and multiplied it by -0.5 or -3, something like that. So you can go through the process to determine if something is scalar multiples of finding the angle between them, but I think that's a little bit tedious. Instead, if you're trying to determine if two vectors are parallel, what I would recommend doing is seeing if one of them can be some constant times the other. So let's look at that with an example. We're going to determine if the vectors are parallel, orthogonal, or neither. So we're going to ask, are the vectors u, which is -3, 9, 6, and v, which is 4, -12, -8, are these parallel, orthogonal, or neither? So if you wanted to figure out if they're orthogonal, that's kind of the easiest one. Take the dot product. If it's 0, great, they're orthogonal. If they're orthogonal, there's no way for them to be parallel or neither. Neither is that special case, and the angle is something different between them. So you can try to find the dot product here, but you're going to see it's a non-zero number. However, because I've been doing this a lot longer, if I look at these values, I see they're all multiples of 3. And here, I see they're all multiples of 4. And if you notice, this is triple, this is double. This is triple, this is double of that first element. So these vectors are actually pretty similar to each other. So because of that, my inclination is telling me that these two things are going to be parallel. So I want to see, are they scalar multiples of each other? So notice what I can do is the vector u, I can go ahead and pull out a 3. And that leaves me with the vector -1, 3, 2. And likewise with v, I can take out a 4, but also all the signs are off, so I'm going to pull out a -4. And what that does is leave me with -1, +3, 2. So these two vectors have the same basis, and I'm just multiplying it by something else. So what I can actually do is to make this vector exactly the same, I would take this and I would multiply it by -3/4, because that will put a 3 out front. So these two vectors are scalar multiples of each other because they're working with that same base vector. So these vectors are scalar multiples of each other. Your vector u is really -3/4 times the vector v. And as a result, because they're scalar vectors, we can say these vectors are parallel. It's the case that the angle between them is going to be pi because one is a negative multiple of the other. They point in opposite directions. So that's kind of the bulk of the cross product. Again, this is going to appear frequently in a lot of operations that we're going to do later on. But what we're going to do soon in the next time is we're going to talk about the cross product. So we're going to see this other multiplication of vectors.